Today we're going to cover sections 18.5 and 18.6, and this relates the cell potential that we did in the last lesson to the free energy and the equilibrium constant, which we covered in previous units. All right, so the equation that is new to us in this section is delta G equals negative N times F times E cell. And E cell is still our standard electrode potential for our reaction. And then F is a new constant. This is Faraday's constant, and it's 96,485 coulombs per mole of electrons. And then N is just the number of electrons that are transferred in our redox reaction. Okay, so let's do an example. And it's important to note that all of the information I just gave you is listed on your equation sheet for the AP test, so you don't need to memorize this equation. All right, so use the tabulated electrode potentials to calculate delta G for the following reaction. So first we have to calculate the electrode potentials. So in this reaction, I2 plus 2 electrons going to 2I minus is our reduction, so that's going to be our cathode, and the reduction potential for that is 0.54. Okay, and then for the anode, we have 2 Br minus going to Br2 plus 2 electrons, and the standard electrode potential for that is 1.09. So if we do cathode minus anode, we get that our E cell is equal to negative 0.55. Okay, and if you remember from the last lesson, a negative cell potential means that that reaction is not going to happen in that direction. But we'll continue with the calculation and see what we get for delta G. So delta G is equal to negative N. In this case, we've got 2 electrons transferred, so it'll be 2 times the Faraday constant, which is 96,485, times our cell potential, which we just calculated, which is negative 0.55. All right, and if we multiply all those numbers, we get a value of positive 106,134 joules, or 106 kilojoules per mole. All right, and so is this reaction spontaneous? The answer is no, and you should know that both from the negative cell potential and from the positive delta G. So remember, a positive delta G is non-spontaneous, and a negative one would be spontaneous or thermodynamically favored. Okay, so just as a reminder, all of these equations are here. They're also on your equation sheet, so you should have no problem referring to those. All right, now just like we could relate delta G and K in our previous chapters on equilibria, we can do the same thing with K and our E cell. So if we know that delta G is equal to negative NF E cell, and is also equal to minus RT ln K, then we can infer from that that N times F times E cell is equal to RT ln K. Okay, and we know almost all of those numbers. Okay, so in this particular reaction, we have 2 half reactions. The anode half reaction, or the oxidation, is copper going to Cu2 plus 2 electrons. And then the cathode reaction, the reduction, is 2H plus 2 electrons going to H2. Okay. The second one here is our standard hydrogen electrode, so that is 0 because that's what we've set it to be. And the one for copper, if we look it up, is 0.34 volts. Okay, so if we plug everything into our equation, we are transferring 2 electrons here, so we have 2 times 96,485 times negative 0.34. Right, since our anode had a cell potential of 0.34, right, and that's going to be equal to 8.314, which is our R, times 298, which is our temperature in Kelvin, times the natural log of K. Okay, so if we solve for the natural log of K, we get, and you do that by multiplying everything on the right and then dividing by the numbers that are on the left, then you get ln K is equal to negative 26.48. Right, and the inverse operation of the natural log is e to the power. So K in this case is equal to e to the negative 26.48. Okay, and if you put that in your calculator, you get 3.16 times 10 to the minus 12th. Okay, so just like you could see from the standard electrode potential, which was negative, this is not going to be a favorable reaction for the products, and that's also reflected in this equilibrium constant, which is very much less than 1, and so it's not going to go very far to the products at all. All right, now that we've linked our cell potential to our equilibrium constant, we can think about this in terms of Le Chatelier's principle as well. So our standard electrode potentials are all assuming a concentration of 1 molar because that's standard conditions. But what happens if we change the concentration? And we could do calculations for this, but that's outside the realm of what we're going to do in this class, but we can make predictions about which direction it's going to shift the reaction. Right, so if standard conditions for the zinc 2 plus and the copper 2 plus for this reaction here are 1 molar, because that's what they are, what if we change the zinc to 0.1, so that's a decrease in that concentration. So if we do that here, that would be a decrease here. All right, that's going to shift the reaction this way, to the right, right? So if we remove product, then we're going to shift the reaction toward the products. And at the same time, if we increase the amount of copper 2 plus, that's also going to shift the reaction to the right. So if we want to force a reaction to go even further to the products, we can do that by increasing concentration of reactants and decreasing concentration of products. So to summarize that, the farther the reaction is from equilibrium, the greater the magnitude of the cell potential. Okay, so that means that we can change the concentrations and get to a place where we're driving the half cell from one side to the other because we're so far from equilibrium. So this is what's used in batteries. This is how rechargeable batteries are used. They have a large concentration of one thing and a small concentration of the other, and then as the battery runs out of power, you get to the point where those two things have leveled off, and you can for rechargeable batteries, you can plug them into the wall and use electricity to run the reaction back the other way and increase the concentration of your reactants again and decrease the concentration of your products, and then recharge your battery so you can do this all over again.